Let's now turn our attention to hydrogen-cooled generators. When the unit size increases above, say, 100 megawatts, hydrogen cooling is normally employed. There are several advantages to using hydrogen as a cooling medium instead of air. Hydrogen is less dense than air, and consequently the windage loss, that is, friction loss due to rotation of the rotor, is considerably reduced. Hydrogen has a much greater capacity to absorb heat than air. Therefore, it is a better cooling medium. The generator operates in a very clean atmosphere. Generally speaking, the hydrogen-cooled generator can be made physically smaller than an equivalent air-cooled generator of the same capacity. Therefore, on the larger capacity generators, it is more economical to install a hydrogen-cooled system, even though this entails a much more complicated installation. The generator casing is built as a sealed unit, with the hydrogen inside the casing maintained at a pressure of about 30 psig, or about 3 bar. Not all units operate at the same hydrogen pressure, so make sure that you know the operating conditions for your particular unit. Actually, the higher the hydrogen pressure, the greater the cooling effect, and consequently the power output of the generator can be increased. The hydrogen is circulated within the generator by shaft-mounted fans, similar to the arrangement for air-cooled generators. The heat picked up by the hydrogen is extracted by passing the gas through water-cooled heat exchangers. Some adjustment of cooling water flow through the hydrogen coolers may be necessary to maintain the optimum temperature for the hydrogen gas. This is normally performed automatically. As the hydrogen is maintained at a positive pressure inside the casing, there is no possibility at all of air entering from outside. This is a distinct advantage, as it ensures that the generator internals operate under ideal, clean conditions. On the other hand, the presence of hydrogen under pressure does have a slight negative factor, that is, the loss of hydrogen by leakage. Leakage could conceivably occur through joints in the casing, particularly around the terminal bushings, but the most likely area is through the shaft seals, and we'll talk more about this in a moment. Generally speaking, the loss of hydrogen is very small, but this still needs to be compensated. Make-up hydrogen is added through an automatic pressure regulator, which is set to maintain the desired internal hydrogen pressure. The hydrogen manifold may be fed from hydrogen bottles or perhaps from a hydrogen tank installed in the plant. In order to prevent hydrogen leakage around the shaft, hydrogen seals are fitted inboard of the bearings at each end of the generator. A common type of hydrogen seal consists of spring-loaded seal ring segments which lightly hug the shaft under spring tension. The segments are lubricated by seal oil, which is maintained at a pressure of about 5 psi above the pressure of hydrogen inside the generator. Consequently, it is impossible for hydrogen to leak out past the seal. Seal oil leak-off is then drained back to the seal oil pumping system. Any hydrogen that may have been absorbed by the oil is drawn off by a vacuum pump, which forms part of the seal oil unit. This small amount of hydrogen leakage is then discharged to atmosphere. The seal oil pumping system is a very important part of the generator operation. It must be placed in operation before the generator starts to rotate on turning gear and then maintained in service at all times. A decrease in seal oil pressure will be alarmed, and the operator must take immediate action to rectify the situation. Usually, a standby seal oil pump is installed, and in addition to this, a DC emergency pump is provided in case of the loss of AC auxiliary power.